Hi, everyone, and welcome to the second day of the conference. My name is Krishi Sharma. I'm a software engineer at an AI consulting firm in the US, Austin, Texas. And for the last 60 days, I've been traveling Europe and learning a ton about the food and culture. But something that's really fascinated me is the differences between the US and the EU in regards to technology and particularly data privacy. I learned that when I was in Munich at the Deutsche Museum. I don't know if I said it right, but apparently there is a German law that prohibits you from taking pictures of people if their faces are noticeable in public. And that's just something new for me from the US. So that's my first taste of some of the stringent laws here in the EU. And then on my second stop, I was in Lithuania, and I started realizing that no matter where I was, there was always a form on the internet that I had to click for cookies. So there's cookie compliance due to the GDPR regulation, I believe. And then yesterday, I was in Brussels walking around, and I happened upon the EU Parliament, which I learned was in Brussels just yesterday. And I saw some notions around the AI Act that is being discussed currently. And all of this made me realize when I saw on the screens in Brussels, all of the different things and proposals, that really all of these regulations, even though it makes innovation kind of hard, is to try to make a better future for technology. And so this is very different for me, and this really helped me understand that even though red tape can be difficult, there are ways to kind of continue past it. So as somebody from an AI consulting firm, my biggest question would be, how do we continue to innovate despite some of these laws that are saying, hey, now we as users get to control what data these companies can take from us. So how do we build AI from sensitive data? So we're going to go on that journey today, and we're going to build, not via code, but just talk about how to build a voice assistant that we're going to name Thierry from using our voice message data on our phones. So we're going to start with the classical ML approach. And we just want to see if there's any way that we can kind of protect data privacy, knowing that there are more and more regulations coming up, and knowing that this is kind of the climate that we're in terms of what people want as well. So with classical machine learning, you have a central server that contains the compute that you're going to need to train your model. And then we have maybe your cell phone and your tablet and your laptop, all with the data that we would need to train our voice assistant. So the data would have to be sent from our devices to the central server, where the compute is, and then some company, like the company that's creating Thierry, right? So that's also us right now. But we would basically collect all of that data and then train one model. So this is fine, except for it has a few limitations. The first is the data privacy. So in countries where maybe you have to ask for consent, you may not be able to get any access to that data, which could reduce the diversity that you have in your training data. The second one is security. So if you're storing all of this data on a central server, then if there's an attack or a data breach, it can be very harmful to your users, but also to you as your company and your reputation, as different companies have seen in the past. And three, it's not very scalable. I mean, it's going to take a long time to train this model as we get more and more data and more users. So then we can look to maybe distributed machine learning to try to see if there's some ways to make this better. So with distributed machine learning, you have still all of your devices with the data, and that data is being collected at the central server again. So it doesn't really do anything for point number one, which is the data privacy component. But we'll see if it does anything better. So with all the data collected at the central server, basically our methodology is going to subset the data and then distribute it across the different nodes in each of those nodes, we'll train a local model. So this should speed up training, but it actually increases the security risk because you have to now go and protect the data across all of the nodes, depending on your infrastructure and architecture. But this will give you a global model. So it is more scalable because you can leverage as many nodes as you want as you grow your users. But in these instances, we're seeing that the data is traveling to where the compute is, meaning that the data has to leave our personal devices. So how can we get the compute to just travel to where the data is already stored? So that's where federated learning comes into play. This was a question that Google researchers had back in 2018 when they first developed federated learning because they wanted to come up with a way that they could continue training and creating AI, particularly in heavily regulated industries like healthcare and telecommunications. In federated learning, you have a similar setup. So you have the central server, and then all of your devices that have the data. But rather than the data transferring to the central server, so being sent off and taken to nowhere land where you have no idea where it is, the data lives on your device, and each of your devices will now train a local model using your personal data. And rather than sending your information or your data to the central server, the model weights are transferred from the device to the server. So each device is going to send the weights from the model that it trained, as well as the parameters and metrics. But it should have no identifiable information. So all of that is collected in the server, and the server then aggregates it using whatever averaging method that you and your team decide on. So we're just going to use a basic one in our voice assistant Thierry. And that will create a global model. So that model will allow us to scale across as many users because it's still actually leveraging the same concepts as distributed machine learning as it's distributing, but rather than distributing across nodes on a central server that some company owns, it's distributing across our own devices. And it also helps us with the data privacy issue, as the data never has to leave the consumer's device. So, it could help with some of the regulations that might stipulate against that. And third, it reduces the need for concern around security around the data because now our server only has model weights and parameters, and it doesn't have sensitive information that could lead to a lot of issues if we don't have the correct networking or if we have a misconfigured firewall. So my team and I at Kung Fu AI used federated learning recently when we were creating a model for a client that we have that could predict breast cancer 5 years before onset. And the only way we could do it was using federated learning due to the HIPAA regulations in the US that prevent you from moving data off of the original server where it's stored. So when we landed upon this approach, we wanted to know what tools would make it easiest to get started, since it seemed pretty daunting to have to set up these kind of networking and communications to send the model weights back and forth on our own. And luckily, there's already a lot of work out there. So we looked at 3 main frameworks. The first one is PySift, which is probably the most popular and well-known. PySift was built originally by PyTorch Lightning, and it can support a few different frameworks, and it has a lot of more advanced settings that maybe somebody who is very detailed in federated learning would be able to leverage. But it isn't as research-friendly, and we were in the research and development phase of our product. So we tried to understand the documentation, but PySift was also going through more changes, so we didn't really use it because it wasn't really user-friendly at the moment when we were developing. So the second tool that we looked into was TensorFlow Federated. So TensorFlow Federated was developed by TensorFlow, Google, and it works very well with the TensorFlow framework, and it doesn't work with other frameworks. It also requires in-depth knowledge about TensorFlow, and at our consulting firm, we tend to use a lot of different frameworks depending on the use case. We also hadn't locked down which framework to use, so we would prefer to use a tool that was framework agnostic. So this one also was abandoned after a few tries. And it was a little while later, after some more Googling, that we found a smaller package called Flower. And Flower, it was developed by a research company actually pretty close by in Hamburg, Germany. And it was framework agnostic, as well as having more of like a research-friendly documentation and tools. So you could easily set up the configuration for the server and the different devices, which are called clients in Flower, without having to know too much about federated learning or having used it, without having had to use it in the past. So our team decided to go with Flower, and it really helped us get started on something that we had never used before. So with Flower, you can just get started with a few lines of code, and we're going to go through that at the end with a little demo. The way Flower works is that you have your devices, which are called Flower clients, and you have your Flower server, which is a central server. And you basically need to send the model weights from the one local model from your first device, or any device that you configure it to the server, so that the server can initialize like a starting global model. That starting global model will then send those weights down to all of the clients, and will kick off training across all of the devices. So training will happen, and then an evaluation step will run. And then you'll get your model weights sent back. So these are like updated model weights now from each of the different devices. Those updated model weights are sent to the server, which then aggregates it using some averaging formula that you've defined. And basically, you kick off a few more rounds. So you can define how many rounds you need. The more rounds tends to lead to better results until like a while when you have marginal return. But it allows for you to get a more better picture of all of the clients' training data and models. So Flower allows for you to define your own metric aggregation formula, which is like, how you're going to calculate your loss, or how you're going to average all of your different metrics that you're tracking for your model, your global model. It also allows you to aggregate your model. So those are like the actual model weights. So you can use like weighted average, federated average, which is just a simple average, or something that you've defined. And then it also allows you to compress those model weights so that you can have a faster transfer between each of your devices and the server itself. Since there's a lot more communication going on, you're going to want it to be faster. So it does that as well. OK, so now it's time for the demo. And I'm going to try to share my screen, so let me know if it isn't big enough. If the code isn't big enough. So what happened? I might also. Do you mind helping me? Sorry, I don't know if I know exactly how you dragged it over. Yeah, on the projector. Then I have an idea. OK. OK, so can you all read this? OK, thank you. So to get started with Flower, you just import it like a normal Python library, and you just define that you're going to start your server. And all you need to do is have your server address and a config. So the only thing you really need to define in the config is a number of rounds, although I do believe there might be a default set. It might be something like 100, so you might want to set it yourself anyway if you're just experimenting. So for this, we're going to do 4 rounds. And 4 rounds is basically 4 rounds of training across all of your devices. And then you can also define a strategy. So we're just using federated average. So that strategy is what the central server will use to accumulate all of the model weights once it's received all of the data, or the model weights from the clients. It's going to use this federated averaging formula, which is a simple average formula that's provided by Flower. And that's how it will determine what the new set of weights is to send back to the clients. So that is how you set up the server. And then for the client, so we, in our demo, are going to use, OK, this is where the bulk of the code is. We're going to use 3 clients, and we're just going to call them 1, 2, 3. That's the device ID. But you basically, so device ID is saying, like, hey, what are the different names of all of these devices that I'm looking out for? The server is going to be listening in on port 8080 for us. That's what we set it for any devices that are trying to connect. So we're going to have to give our devices the server address so that they know what to reach out to. And we're also going to have to provide each of our devices or Flower clients a model for local training. So the model is, we're just going to use a simple MNIST model, and I'm not going to really review this one too much because it's more around how to create an ML model and not necessarily federated learning. But you can see here that you have, the model creation and all of the data splitting and the model fit, which is the important part. So those are the key components. Before we run it, I will also show you, I just set up like the server config. So you can set up how many clients that you want it to fit on. And if you end up having like 100 devices, 1,000 devices, you can say like, hey, I only want a fraction of this, and that allows for you to have faster training. So you don't have to wait for every single device to connect in case some are having networking issues. So with this, we're going to start our server. And I think this might be too small, but so if you can't read it, basically it's saying, that Flower is starting, it's initializing global parameters, but for it to set the initial parameters, it needs at least 1 random client. So this means our server is up, but we need to get at least 1 client up. So we're going to use this shell script that I created, which basically just uses Docker to kick off a client using the client.py script that I showed you earlier, or that's up here. And we're going to give the device ID of 1, since this is set to listen to whatever I put in the terminal. So this is just downloading the data. That's how I set it up, so it can download it and split it each time. But basically, once this runs and trains the model, it's going to send those parameters back to our server, which will acknowledge the fact that it now has parameters and is ready for the other devices to connect to it. So it's saying that it's connected and that the server is now ready. So the server says that it's received the parameters, it's evaluated it, and federated learning is starting. But really, when it says FL starting, normally my team knows that it still needs to connect to other devices. So I think it's kind of like not exactly accurate. But it's ready to start is kind of what it means. So we're going to run our next 2 clients. And both of these should kind of give similar messages in terms of connecting to the server and being able to send their weights back and forth over a few rounds. So it'll probably take a few seconds. But at the end, we should see that once the clients have connected to the server and the training has finished the 4 rounds, the server will automatically close the connection. OK, so this time it is able to move past that connectivity step, and you can see that each round it's calculating the different metrics. I can try to make it a bit bigger, but I don't really know how to make the terminal bigger besides this. Is it OK? It's Command plus. No, thank you. Well, all this code is up on GitHub, so you can also run it locally and see the exact logs. But it's basically telling you the metrics for each epoch for each training round. So if there's 5 epochs, that's how I set it, and all of the 4 training rounds. And then on our server, we see that it's been able to calculate the metrics. It's telling us that the loss is minimizing over each of the 4 rounds, and that it's finished and the server has exited. So now I need to go back to the presentation. OK. So to further improve our model that we're creating, we could add more clients and different data sets, which would increase the diversity of our training data. We could also optimize the hyperparameters for the models on each of the clients. So the models that are training locally, that's typically called client side. You could kind of twist or configure the different knobs on that to make the model itself better. And then you can also test out the different model aggregation techniques on the server to figure out if there's a better way to average the model weights and then send them back down. So overall, federated learning provides a secure way to train the model, and it allows you to have faster predictions because the predictions are going to happen straight on the device, and it doesn't need to go and contact some central server. It also lends to a diversified training data set because now you can actually access greater sets of data that you might not have access to either under regulation or consent, or because it didn't fit the exact parameters that you would need out of a data set for your training data set through classical machine learning. There are a few drawbacks, and this is something that I think more research and more use would help with, but you're constrained to the compute resources on each of the clients. So if there's not enough compute on your device, then you can't really train the model on there. You also need fast and reliable networking. So if you have no internet, then you can't communicate to the server to send the model weights, which is a problem. And then you also don't have any access to that data. So you can't label it and you can't clean it in the way that we're traditionally used to with machine learning. But all of that to say is that there's still the ability to do digital transformation with these regulations, and we can still continue to improve on technology, even though it may feel like sometimes red tape makes it harder. So that's the end of my talk. And the first link is to GitHub, where this repo that I used for the demo is online, along with the shell scripts and everything that I used. So if you're interested in trying it out, I would definitely copy that down. The second one is just a link to my personal website and contact. And the third one is a link or the actual website URL for my company, kungfu.ai. So yeah, I'm open to questions.